Hello, everybody. Welcome, welcome, welcome. We are on record now, and we are at 6 o'clock. So lots of things to get done today. We have a test scheduled before the end of this evening, and a lot to talk about with respect to parallel and series parallel circuits. Let's take a look here. There's a chat. Hello, Ephraim. Glad you can make it, and hello to everybody. Fantastic. So let's go ahead and get started with this. We will begin with Canvas, and on Canvas I happen to have an introduction to series parallel circuits. And let's talk about, actually let's do a parallel analysis first. So I'll go ahead and go to make sure my camera is in the on position. Here a moment. Okay. And Pete, that's great. Make sure I've got a focus on here. Could someone mute the microphone? I hear water running in the background, and I don't have any loose plumbing in my house. So if you would be kind enough to mute your microphone, that'll help a lot. So let me get focused. Focused. Click. Cool. All right, let's get focused on this. So what I'd like for you to do, let's get started with a VIR chart. We'll skip the power for right now. Let's go ahead and do a V, an I, and an R. Four rows for three resistors. So I will have an R1, I will have an R2, I will have an R3, and totals. 3 columns. And from what it is that you recall from before, VIR, our focus is really on each row that pertains to some values that I'm going to give you in a moment for us to do the analysis. So the analysis in this particular case will be, I'm going to do it this way, something that you don't see in a textbook. But let's go ahead and put the voltage there. Let's go ahead and jam a resistor here. Let's go ahead and jam another resistor here. And I'm going to go ahead and jam one more resistor over here. Okay, this will be R1, this will be R2, this will be R3, and my voltage VS. And I'm going to give you this information. I'm going to say that R1 is going to be this. So R1 is going to be yellow, violet, brown, gold. R2 is going to be brown, black, red, silver. R3 is going to be orange, gray, brown, and gold. So I'm going to give you those color codes. I'm going to tell you that the voltage source in this case happens to be 12 volts. Your task is to fill this in. So you're going to have to do some deciphering. You're going to look at this. These are all 4-band resistors. And by now you should all have a comfort level as to how to decipher your 4-band resistors. First band, first digit. Second band, second digit. Is my third band a third digit, yes or no? General question to everybody.
No.
Third band is not third digit in a 4-band resistor complement. What does that third band represent in a 4-band resistor color scheme?
The multiplier.
multiplier or simply number of zeros. It could be a power of 10 multiplier or number of zeros. So go ahead and take 1 minute to decipher these. Go. And aren't you glad you happen to have your handy dandy notebook? And in your handy dandy notebook happens to be all of your pertinent information. Let's see, we have atomic theory, we have law of electrostatics, we have Ohm's law, electrical terms. Oh yeah, isn't that nice? You have resistor color coding in your notebook. So you don't have to go look on Canvas. You don't have to be digging in on the internet. Everything should be in your journal, notebook, composition book, whatever you want to call it. It should be here.
Hey, Frank, can you read the third one, the resistor? I can't really see it.
The third one is
Green.
Orange, gray.
Orange, gray?
Let me speak. Orange, gray, brown, gold.
Thank you.
Thank you. So aren't you glad you have your stuff handy dandy written in your notebooks, journals? All right, let's take a look and see what we got. I will be calling on classmates. Let's take a look. Anna, did you decipher R1, please? What is the R1 that you decipher?
I got 470 ohms.
You have 470 ohms. Before I commit to writing that down, because I am using ink and not paper, who else agrees that R1 should be 470 ohms? I see a few thumbs up. That's good. You can do thumbs up on the Zoom. So I will put down 470 with the omega. Very good. And on the VIR chart, we don't have to write down plus or minus 5%. Tolerance is not part of our VIR chart for now. So we're really looking at the first three bands. Thank you very much, Anna. Next one goes to Erica. Erica, do you happen to have the coded value for R2, brown, black, red, silver? And we would want this in proper engineering notation, yeah? What do you think, Erica? Erica, are you with us? She might have stepped away.
Sorry.
Yes, I'm sorry, go ahead. You have the coded value in proper engineering notation for R2. What did you decipher?
I got 102 ohms.
You have 102 ohms?
Yeah.
Okay. How many people agree with 102 ohms? Give me a thumbs up. And as I'm looking at the matrix screen, I don't see that. Okay, let's review this. Remember, in a four band sequence of resistors, if I go to look at my handy dandy notebook, journal / whatever you want to call it, and I go to the page that has resistor color coding, and I look at resistor color coding, and I look specifically in my notes for four band resistors, it says specifically, and then we'll go ahead and go to speaker view so you can see this a little more clearly. My first band is my first digit. My second band is my second digit. My third band is not a third digit. My third band is number of zeros. The fourth band would be tolerance. So you called out the first two bands correctly, as clearly as a 1 for brown and a 0 for the second band. But the third band is not a third digit in this particular case. It would be if we were dealing with 5-band resistors. So in a 4-band resistor, Erica, you want to try that third band again? What do you think this would be? This is a 1 and a 0, followed by how many zeros?
Is it 1K ohms?
You're correct. It's followed by 2 zeros, and the proper engineering on here would be 1 kilo ohms. Excellent. This would be a 1 and a 0 followed by 2 zeros, which would be 1,000. And we'd never write down 4 numerals in front of a decimal point. We have to write proper engineering notation, and it's going to be 1K ohm. Very good. Thank you. And the last resistor, R3, let's go ahead and take a look at R3. Andrew, do you happen to have the coded value for R3? I haven't.
Yeah, I got 380 ohms with a 380 ohms.
Okay, how many people will give me a thumbs up on 380 ohms?
And also a tolerance of plus minus 5%.
Plus or minus 5%. So let's take a look again. Let me look at the grid. Everybody can see the grid. How many people agree with 380 ohms gives us a thumbs up? I see. Okay, you have a few thumbs up. All right, it is in fact 380 ohms. Very good. So these are your freebies. These are the givens, and you have to decipher these properly, because if any one of these is deciphered incorrectly, it would throw off your R total, which would throw off everything else. It would be horrible. Okay, so we have to be very careful when we decipher resistor color codes when we put them into a VIR chart. Okay, now we're happy with these. We've confirmed 470, 1K, 380 with a 12-volt source. We still can't apply Ohm's law yet. Ohm's law right here, says we need 2 quantities in order to calculate a third. We only have, if you look at the first row, we'll go back to a speaker view. If you look at the first row, I only have 1 quantity. Second row, 1 quantity. Third row, fourth row, only have 1 quantity in each of these rows. I need to somehow get a second quantity in one of these rows. What can I do? Who has a suggestion?
I do, Professor Co.
What do you think?
You want to add up all of the ohmic totals on the resistant column.
Oh, okay. So we want to get an R total is what you're saying, yes?
That's correct.
Okay, we need an R total. This would be a good one to fill in. This would be a very good one to fill in, because if we have an R total, wouldn't we be able to get an I total? Yes, we would. Okay. Then could someone else volunteer the method by which we will determine an R total? What method would we use to determine an R total? Who would like to volunteer a suggestion on how we determine that? Carlos, you can unmute your microphone and volunteer. I can't see everybody else.
Yeah, you add the resistor values and you get the total resistors value at the, the totals row. Was that the question or no?
Add them if we, would we add them if we had, yes, we would if they were in series, yes? Because here, take a
yeah,
look.
that's right, sorry.
Yeah, so for a moment, let's just go ahead and share screen, and let's go ahead and share this screen for a moment. And share. You should all be looking at my PowerPoint screen, yeah? And as you're looking at my PowerPoint screen, we have series circuits and the characteristic formulas for series circuits. And if you look at our total formula on the right-hand side of this slide, it clearly says our total is equal to R1 plus R2 plus R3. You add them up. But the slide is titled series circuit. Do I have a series circuit on my paper? The answer is no. So we really need to look at this slide, which is parallel circuits. Is everybody able to see my parallel circuit slide? And in parallel circuits, do I have an RT formula? Yes, I do. And the RT formula, as we've explored before, was to calculate using reciprocals. There's a couple of guiding principles about this that you should always remember. So as we look closely at the slide, look at the fourth bullet point. Let's see, RT. Yeah, talk about current flow. Okay, let me explore a little further down the way. And all right, yes, I will go to here. This is what we did last week, actually. So let me go to week 3 PowerPoint lecture. And on week 3 PowerPoint lecture, it's coming up because I expanded on parallel circuit discussions. And right here. All right, we define parallel as devices are in parallel if and only if the leads on one side of these devices meet at a common node and the leads on the other side meet at a different common node. Look at point number 5. It says RT for parallel will always be what? Less than the lowest ohmic branch. Does everybody see that? Okay, RT will always be less. And we want to calculate the RT. I won't review these calculations with you because we did that last week and you had homework in making these calculations. So suffice to say, we have some guiding principles. The RT here must be less than the lowest ohmic branch. Which one of these is the lowest ohmic branch? R3. And so RT must be less than this. So we need to calculate R total. And how do I calculate R total? The keystroke sequence for R total is equal to 470. And then I'm going to hit what key? It's called reciprocal. And I'm going to add that to 1 EXP 3, because that's my kilo. And I have to hit reciprocal. And then I have to hit add. Then I'm going to bring in the third one, 380, hit my reciprocal key, hit equals, hit my reciprocal key one more time, and hit equals one last time. That is your keystroke sequence using our handy dandy wonderful under $10 calculators. So I'm going to calculate this on the side. 470 reciprocal plus 1 exponent 3 reciprocal plus 380 reciprocal equals. Hit my engineering key, probably would be prudent at the end of the sequence, as our calculator will do this. And I'm going to ask if, Ryan, do you happen to have the calculated result for these 3 resistors in parallel? What are you calling out? What are you going to commit to?
I have 173.63 ohms.
How many people agree with Ryan? Give me a thumbs up on the screen if you agree 173.63 ohms. See thumbs up all over the place. All right, 173.63 with the omega symbol, okay? And if anybody, you shouldn't have any issues calculating this value. You've done it during the homework. You've done it this past week. If you've had any questions, what is your resource? If you have any questions on this calculation sequence, you go to Discord. It's the fastest way to get some kind of feedback from your classmates and also myself. Now that we have this and we're happy with this, we should probably calculate this one more time. Everything else in this table depends on this being correct. So why don't we just do this again, clear the calculator, and punch this back in. 470 reciprocal plus 1 exponent 3 reciprocal plus 30 reciprocal equals engineering. We're happy with the result. Bingo, done. Now, what would be the next step in this exercise. We filled in the R column. Now we still have 7 more boxes to fill in. What would be the logical next step? Question goes to Frank Sepulveda. What would you do next?
12 divided by total ohms.
Oh, 12 divided by total ohms. You're going to apply Ohm's
Yeah.
law to find this current, yeah? So,
Yeah.
okay, that would be a good approach. Let's go, all of us, calculate 12 divided by these total ohms, and I'm going to ask for that result from Benjamin. Do you have that value for us for current? Benjamin.
Yes, sir.
12 divided by 173.63 ohms. What do you calculate for current? Benjamin. Benjamin, are you with us? Your microphone is muted.
I get 69 0.11 kilo ohms, milliohms. Sorry,
What's your power? What is your power of 10?
10 to the negative 3, so milli.
Okay, so why don't you read the whole thing out?
69.11.
Well, 69.11 what? Apples, oranges, and I'm looking for
Oh,
an engineering prefix, and I'm looking for an
69.11
electrical unit. So
milliohms.
go ahead and read the whole
Milliamps,
thing
sorry.
out.
69.11 milliamps.
Perfect. That's how we speak the answer. How many people agree with 69.11 milliamps? Give me a thumbs up. Cool. 69.11 milliamps. Very good. Outstanding. Thank you so much, Frank. Now, we
Professor
have
Coe,
6
can I
more
ask a
boxes
question?
to fill in. Okay, 6 more boxes to fill in. Whew. How are we going to fill in these 6 boxes? Who has an idea they would like to volunteer?
Is voltage constant in a parallel
All the
circuit?
same. Yeah.
So Javier is asking, is voltage constant in a parallel circuit? Well, if we have it in our notebook, and if we also got this information from our previous slide set with this guy right here. So take a look at the parallel PowerPoint slide. Is there a formula? Well, here, the third bullet point on the left-hand side. What does it say? Third bullet point on the left-hand side. It says, what is the same across all branches of a parallel circuit? It says clearly voltage is the same. Is there a formula on the left-hand side, right-hand side, expressing the relationship of voltage? Does it not say that total voltage is the voltage of the first branch equals voltage of the second branch equals voltage of the third branch? This is what our slide tells us. So if this is what our slide tells us, what do we do in this particular case for our chart? Javier?
Oh, you put 12 for all of them?
We write 12 volts for this entire column. It's one of the easiest things to do is to solve a VIR chart for a parallel circuit, because the voltage is the same across the branches of a parallel circuit. Everybody clear on that? Now that we have this information, do we have enough information to calculate the currents? Again, we would apply Ohm's law. So I would like each of you to calculate the current IR1, IR2, and IR3. Give you a minute to make those calculations, and I will do the same on the side. I will be calling out for those answers in just a moment. I'm going to call out some of our friends here. Let's see who's available. Tony, we haven't heard from you yet. What is your calculated value for IR1? Tony, unmute your microphone.
Oh, 25.53 milliamp,
How many
53
people
milliamp.
agree with How many people agree with 25.53 milliamps? Several thumbs up. 25.53 milliamps. Very good. Thank you very much, Tony. Next one. Could I have the calculation for IR2? Harpreet, what do you calculate for IR2?
12 milliamps.
How many people agree with 12 milliamps? Raise your hands. Cool. 12 milliamps. And now we want IR3. So IR3, could you give that one to us, please, Gregory?
31.58 milliamps.
How many people agree with 31.58 milliamps? Give me a thumbs up. 31.58 milliamps. And how can we verify that these currents are correct? Because they're not all the same. When will current be the same in a circuit?
Series circuit.
Series.
In a series circuit, current will be the same. In a parallel circuit, voltage is the same. So in a parallel circuit, current has to be different. And so how do we know these currents? Is there some way to determine that these currents calculated correctly? Yes or no?
Yes.
What would be one way?
You add all the currents and make sure it equals a total.
If we add all the currents, if I add the first branch current and I add the second branch current, will I get the total? And the answer is yes. When I add all the currents together, they will add to be the total, okay? There's another double check. Just because the numbers add up is one thing, but are the numbers in the right place? Meaning, if you go back to the share slide, now we'll go back to the share slide, and there's a concept that was very important on the share slide with respect to parallel circuits, and that is this. On the share slide, take a look at this. Does the largest ohmic resistance, in fact, flow the lowest amount of current? The largest ohmic resistance, does it flow the lowest current? So on your table, which is the largest ohmic device? Isn't that R2? And does it in fact flow the lowest amount of current of 12 milliamps? The answer is yes. We have proportional distribution. Take a look at the next sentence. The next sentence in the slide says what? It says that the highest ohmic resistance will flow, the smallest ohmic resistance will flow the highest current. Which one of these three resistors is the lowest ohmic device? Isn't that R3 at 380? And does R3 in fact have the highest current? The answer is yes. Okay, so are we happy that the numbers not only add up, but are we happy that they are proportionally distributed? Yes, proportionally distributed. Very good. Any questions on solving a VIR chart for a parallel circuit? Okay, I hope that would be fairly straightforward. Okay, we're into a new territory now, and the new territory is to bring us into the world of series parallel. And let me get to that. Okay, so go here and go here and go here. And we will share. So in week 4, Canvas, one of a number of different Canvas pages that we have planned for you for this week, is a PowerPoint on series parallel circuits. So I will go ahead and let's go home and good. We are here. There, open it up. Boom. All right, let me go to the share screen and share. I want to share this guy and share. Okay, And let's go ahead and make this a little bigger. Okay, everybody see this pretty large? So we're talking about series and parallel circuits, how to find total resistance, current, and voltage. Some of this is repeated information. So we started off with series circuits, and with series circuits is the easiest. So if I happen to have three different resistances, 20, 30, and a 40, we combine them by addition, and we'll end up with a single equivalent or total resistance of 90 ohms. When we play with parallel circuits, we happen to have, as they say, two common connection points with another component. So all of these components are connected at the top at a common connection point, and all of these are connected at the bottom of the resistors at a different connection point. And it reminds you that, no, you can't just add them together. So what do you need to do? You have to calculate these in parallel. So everybody take these 5 resistors and give me an R total. So go ahead and do that calculation right now. 5 reciprocal plus 14 reciprocal plus 21 reciprocal plus 25 reciprocal plus 100 reciprocal equals, and you end up with some value, and I'm going to call some lucky soul here in a moment. So look at those 5 values, punch them into the calculator. I'm looking for an R total for these 5 resistances in parallel in proper engineering notation with 2 digits after the decimal point. That is our standard for our work. Okay, question is asked. Jess, do you have a calculation for us for the total of these 5 resistances, please?
I'm actually still working on it.
Okay. We punch in 5 reciprocal plus 14 reciprocal plus 21 reciprocal plus 25 reciprocal plus 100 reciprocal equals reciprocal.
So I have 2.71 ohms.
2.71 ohms. How many people agree with 2.71 ohms gives us a thumbs up? Cool. 2.71 ohms would be correct. Thank you so much. We use reciprocal method. And when we go to do so, this sequence will calculate to be 2.71. The slide doesn't use the same standard of calculation as we do. That's a little less. They're rounding to the 10th. We round to the 100th.
Professor Coe, can I ask a question, please?
Yes, please.
So in the homework, there were the 2 pages of these calculations.
Yes.
And the method that I'm using is the 1 divided by parenthesis and then dividing each resistor by 1. Is that okay instead of doing the reciprocal method?
It's a few, oh, that's perfectly fine. It's a few more button pushes.
Yeah, I don't know. I find it, because you know my math, I just find it easier for me.
That's fine. Yes,
okay.
no, each of you will use the method that's easiest for each of you. What's interesting is in the classroom, as I'm watching students do this calculation, I notice some students have the 1 finger method. 1 finger, their pointer finger of the right hand or left hand, whatever the dominant hand is, and they're punching the keys on the calculator with 1 finger. And then I have other students that are using the double thumb method, and they're doing thumb, 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 the same way that they do texting on their cell phones or gaming. And so if it's comfortable for you to use the 1 divide by method, you're punching more keystrokes, but that's okay. Whatever method you develop that gives you what we call finger memory, go for it. Okay, because that will be your learning method. Nothing wrong with that technique as long as you end up with the same end result. Did that answer your question? Cool. Now let's take a look at series parallel. Here's where we jump into something a little more interesting. it says if we combine a series circuit along with a parallel circuit, you have something that is known as series parallel. Then if you look at the drawing, it says R1 and R2 have what relationship to each other? They're in parallel. And the notation, and I've shown you this before, the double vertical lines right here in this part of the slide, the double vertical lines is the symbol for parallel. It means R1, you would read this as R1 in parallel with R2, okay? So, and then that happens to be in series with R3. As you look at this, it says the sequence for solving this is, what do you need to do? You need to calculate these two guys in parallel first before you add to the R3. In other words, you have to combine these two, simplify them into a single resistance, and then you can combine to this in order to get a total ohms. Could we all do this, please? Could you all calculate 27 ohms in parallel with 34 ohms? Everybody do that now. Clear your calculator, take 27 reciprocal plus 34 reciprocal equals, hit engineering. I'm using the two-thumb method. And in doing so, let's see. Luis, we haven't asked you yet. So what do you think the R1 parallel to R2 works out to be?
I got 15.05 ohms.
How many people agree with 15.05 ohms? Okay, so very good, very good. We have 15.05 ohms, and you have to think about this before you write the number down. Just because your calculator spit out a number, don't just write it down. It has to make sense. And so, first of all, does the total of a bank, a pair of parallel resistors form a bank? Bank is the nickname for parallel circuits. Does the total for the bank turn out to be less than the lowest ohmic branch? The answer is yes, because the lowest ohmic branch in this case is 27, and you calculated 15.05 ohms. Seems reasonable, okay? All right. Now, since this is a critical calculation that you're going to need to add to R3, maybe it's a prudent thing for you to exercise those thumbs again, clear the calculator, and recalculate it one more time. 27 reciprocal plus 34 reciprocal equals, hit engineering, get used to doing your double checks. And as you get used to doing your double checks, do you confirm that that pair is in fact 15.05 ohms? Everybody good with that? While that number is on the display of your calculator, it's now in series with the 58. Can we just add this to the 58? And what would be the sum total of resistance in this three resistor arrangement? The question would go to Ephraim. Are you driving, or are you safe where you are now? Ephraim? Do you have an R total for us? He might be driving. Kirsten, do you have an R total for us?
73.05 ohms.
73.05 ohms. How many people agree? Give us a thumbs up. 73.05 ohms. Okay, so as you look at this series parallel, again, why is it called series parallel? Is part of this series, which part of this series is in series? Clearly R3. It's a single path to the source. It's a single path from the source. R3 is in series with what? It's in series with a bank. The bank is made up of a pair of parallel resistors, and that's R1 and R2. So since part of the circuit is in parallel, part of the circuit is in series, this is called a series parallel circuit. Everybody okay with the terminology?
The total was 73, you said?
73.05 ohms.
Okay. Right.
Okay. Because the bank was 15.05. So if the bank was 15.05 ohms, then when you add it to the 58, you get 73.05 ohms. Okay? Okay. All right. Now, let's go ahead and see. They're using product over sum. They calculate 15.05 ohms. Add with 58, there's your 73.05 ohms. They round off to 73, but we round to 73.05. So we end up with the same, essentially the same calculated result. So far, so good. Now let's continue. We want to find I total. If you want to find I total would be 100 volts divided by your total ohms. So let's, as accurately as we can, let's take our 100 volts and divide by 73.05 ohms. Let's do that. 100 divide by 73.05 ohms. We'll put in the 05 because we calculated that. We wrote that down. And you will calculate a current. And the current works out to be pretty much what they have down is 1.37 amps. How many people agree with the calculated current that's on the slide? Good? Okay, very good. Now, I've got a question for you. Can we determine the current that is flowing through R1 and R2? That's a very interesting proposal. Can we determine the current that is flowing through R1 and R2? So let me do this. And if you take a look at the voltage source, interestingly, how many plates is shown in this voltage source? It shows a complement of 6 plates as opposed to 4 as opposed to 2. And I said this was perfectly valid for a voltage source to be shown with 2, 4, or 6. All right, so we have R1 of 27 ohms. We have R2 of 34 ohms. We have an R3 of 58 ohms and a 100 volt source. Okay, so this is what I'm going to propose for us to do. I'm going to stop sharing on this particular slide.
Can you repeat?
And,
Professor Coe, your microphone's breaking up.
okay, let me just change. Let me go to here, speaker view, and let's go here, and we'll go ahead and use this microphone. We'll change the microphone. All right, can everybody hear and see my paper? Can you hear my voice and see my paper? Yes? Cool. All right. That being said, we are again going to do a VIR chart. We have 27 ohms here. We have 34 ohms here. We have 58 ohms here. We calculated 73.05 ohms here. We have a 100 volt source. We calculated 1.37 amps over here. And this is R1, this is R2, R3, and total. So what happened in this particular circuit, anytime you're working with series parallel, is you want to do this. You want to do something known as a redraw. We're going to redraw this down here. And that means directly below the circuit, I'm going to copy the voltage source. I'm going to come up here, and I'm going to call this point A. I'm going to call this point B. So here is a point A, and here is a point B. And in between happens to be a resistor. And over here happens to be another resistor. This is my original R3. This is my 58 ohms. This guy here, I've done in green. This guy has a name, and I'm going to name it. So as you look at this, I'm going to name this REQ1. So EQ stands for equivalent. So this is our equivalent number one, meaning this guy happens to be R1 in parallel with R2. And that's the equation that I will use. And I'm not going to call this RT because RT is 73.05. This REQ1 is in fact RT for the bank, but it is not RT for the whole circuit. So I don't want to call RT more than one place. I'm going to call this REQ1. And we calculated this earlier. We calculated this to be equal to 15.05 ohms. Okay? And we're still dealing with a 100 volt source. All right. So the question now is, how do I fill in the rest of this? Let's think about this. Let's think about this. Could I take this voltage and fill in the entire column with 100 volts? How many people would give me a thumbs up of taking this voltage and filling in the entire column of 100 volts? Thumbs down? No, I see some thumbs down, no thumbs up. Yeah, a lot of thumbs down. How about this? And let me ask another question. How about, since you calculated a current, 1.37 amps, how about we take that 1.37 amps and fill in the entire column? That you found one current, all the currents are 1.37 amps. How many people would give me a thumbs up there or a thumbs down? Thumbs down. Ooh. So we cannot use those norms of all the currents being the same because this is not a series circuit. Part of it is in series, but the whole thing isn't. We cannot use the norm of finding one voltage. We found all the voltages because part of this is in parallel, but not all of this is in parallel. So we have to do something else, don't we? There's a number of ways of doing this, and any of those numbers of ways is fine. I'm going to show you something here called CDF. I introduced you a couple of weeks ago to VDF. And what do you recall VDF was? If you look up VDF in your notebook, what do you recall VDF to be?
Current divider.
Good, I'm hearing a lot of shout outs, that's fine. Voltage divider formula. Well, I'm going to call out CDF. What do you think CDF stands for?
Current divider.
Current divider.
That's good. Current divider formula. Current divider formula. Okay, let me go back to speaker view so you can see my paper a little better. And current divider formula. Now the standard format for this formula is this. IRX, meaning the current some unknown resistor, will be equal to the RT of that bank divided by the RX in question times I total. That is your general form of the current divider formula. In this particular case, even though the formula says R total, am I going to use the 73.05 ohms, the total for the entire circuit, or does current divider only pertain to the bank of parallel resistances? Which am I going to use? Am I going to use, for this RT, am I going to use the 73.05 ohms, which is R total for the whole circuit, Or am I going to use the R total for the bank of parallel resistors? Who's got an opinion? Jess, what do you think? I saw a hand raised.
Yeah, I think you would use the total for the bank, which is 61.
The total for the bank, which would be the 15.05 ohms. How many people agree with that? How many people agree, and give me a thumbs up if you think that's right, that our total for this particular formula for current divider is not the 7305, our total for the circuit, but should be our total for the bank of 1505 ohms. Raise your thumbs up if you agree. Thumbs down if you disagree. Wave at me if you're not sure. There's a few not sures. Okay, let me clarify this for you. This R total, this is called what? Current divider formula. Current divider formula is only applicable for the parts that's in parallel. You don't use current divider for an entire series parallel circuit. So CDF is only for parallel circuits. So the RT in this case, my friends, is only for the R total of that bank. We calculated the R total for this bank. We calculated the R total for this bank as being 15.05 ohms. So let me write down the specific formula for you. If I want IR1, then it will be my REQ1 over R1 times I total. In this particular case, this is going to be equal to 15.05 over 27 times 1.37 amps. Do this math. 15.05, which is the total for the bank, divide by 27 and multiply that by 1.37 amps. And I am looking for a calculated value. That calculated value, please, will come from Abbas. Do you have that number for me, please?
It shows me 763.65 a micro. Oh wait, did I get it wrong?
Is it micro?
Hmm?
Is it ohms?
Yeah.
This is current divider formula. So is current measured in ohms?
Yeah.
I don't think so.
I just measured in amps.
Is measured in amps. Okay. And what is my engineering prefix?
It's a -3.
Okay. So what is the prefix then?
The prefix is milli.
Mm-hmm. Correct. So in your handy dandy notes, you should have your engineering prefixes, yeah? And in your engineering, mute your microphone, Abbas.
Oh, sorry.
Okay. Okay. So in your engineering, mute your microphone. Okay. In your engineering prefixes, as part of your notebook, you should be able to see 10-3. 10-3 is spoken as milli, and you use what symbol? A lowercase m. Then in your notebook, you should also have, for electrical terms, that your current symbol is I, the units are amperes, and then the symbol for amperes is A. You also have this in your notebook. So you go to one place for quick reference of your information. It should always be there in your journal, yes? So that having been said, this works out to be your 763.65 milliamps. How many people agree? Thumbs up. Cool. All right. So this is what's happening. Watch this very, very carefully. I have in the schematic a negative plate here. I have a positive plate here. So the top of this circuit, the top wire here, point A, is attached to the negative plate of the voltage source, which means the top of these resistors, the top of R1 and the top of R2, is attached to the negative plate. They share that polarity. So the top of R1 and R2 must be negative, which makes the bottom of R1 and R2 positive, right there and right there. And if we follow the flow, the top of R3 should be negative, the bottom of R3 should be positive, right there. And do I have the bottom of R3 connected to the positive side of the source? Are these two ends sharing the same polarity? Yes, positive plate, positive end of the resistor. And if I trace the path for current to flow, well, let's see, we calculated I total. I total is the current that leaves the source, comes up here, turns around, and we calculated an I total that was equal to 1.37 amps. If that is the current that leaves the source, this must also be the current that returns to the source. What leaves the source, so your I total is equal to 1.37 amps. What leaves the source has to return to the source. Can I see from this what current flows through R3? Can I see the current right here that flows through R3? What is my current through R3? Do I have to calculate that current through R3 just by looking at my drawing? Question goes to Ephraim. Ephraim, are you there? Ephraim. So what is my current through R3, sir?
R3 is 1.37 amps.
And that's not calculated. That was part of our previous calculation. That's 1.37 amps. If you look at my redraw, here is negative, here is positive. And if I look at the redraw, this part is negative, this is positive, this is negative, this is positive. My electrons flow up, go over, come down through here, come down through this, wraps around, goes here, goes back up to the source. I clearly have 1.37 amps flowing through one of the original circuit resistors. I didn't even have to calculate that. Once I calculated IT for the total circuit, if that's in series, the R3 is in series path with that current, it will share that same current. I just need to decipher the currents between these two paths. So right now, at the top of the circuit, I have 1.37 milliamps flowing into this bank. Part of this current will split in this direction, part of the current will split in that direction. We decided through current divider formula that this is 763.65 milliamps that flows down through R1. Something must flow down through R2 in order to combine at point B to come out to be 1.37 amps flowing through R3. How do I find this last current? Who has got a suggestion? Question goes out to the gallery. Who would like to volunteer a suggestion of how to calculate this remaining current, that current right there? Yes, Jess, what do you think?
Could you subtract it?
Could we subtract it? That would be a valid method. If I know the current coming into the bank is 1.37, and I'm confident that the current that flows through this branch is 763.65 milliamps, I could subtract this from the totaling in and find the difference. That would be one method. It's a valid method. Who has another method?
I do.
What
Can
do
we
you
use
think, Ephraim?
the current divider formula?
Current divider formula. We could use current divider formula again. So instead of IR1 in this formula, we would put an IR, we would put an R2 and an R2 in this formula. So could we, let me go ahead and use a slightly different color. If I want IR2, could I take the 15.05, let me go ahead and go to speaker view. Could I take the 15.05 and divide by my 34 and multiply this by 1.37 amps? Could I apply current divider to the second branch? That would be another equally valid method. Okay, so why don't we practice the current divider? Go ahead and take 15.05, divide by 34 times 1.37. Everybody do this calculation, and I will repeat that if it's a little small on your screen. I apologize. Take 15.05 and divide by 34 and multiply by 1.37. And you all can hit engineering. And what does Gregory, what do you calculate, Gregory?
I got 606.42 amps.
Milliamps. Milliamps is correct for engineering and the electrical term. 606.4 what?
606.43 milliamps.
Ah, that's what I thought you didn't say. Okay. 606.43 milliamps. Again, you have to be mindful how you round, because it is, if you look at my calculator is the same as yours. It's a 606.42641. That third digit, that 6, compels you to round the 0.42 to become a 0.43. Everybody clear on that? And if you don't do this on the test later, that would be an error. You have to round properly, and you have to call out the engineering properly. This is 10⁻3, so you would call this out as, in fact, milliamps. So how many people agree with 606.43 milliamps? Give me a thumbs up. Cool. Okay. So we calculated this using current divider formula. Why don't we go ahead and try the subtraction method? Let's go ahead and try the subtraction method that was suggested by another classmate. So let's clear. We have the 1.37 amps coming in, and we're going to subtract the 763.65 exponent -3 milliamps that goes here, and let's see if we end up with something on our calculators that is close to this. Boom, and hit engineering. Wow. It's not far away, but there's a slight difference. And why is there going to be a slight difference between the 606.43 milliamps and what my calculator is showing, 606.35 milliamps? Who can tell me why we have a difference? Did we make a mistake?
You're using a rounded number?
We're using a rounded number. Correct. We're using this rounded 763.65 milliamps. It actually was many, many digits. We wrote down a rounded number. We used a rounded number. We're going to get something that is going to be a little bit off. This particular one is a little closer. The bottom line is, do these two currents add up to give me the 1.37? So let's go ahead and clear, and let's go ahead and punch in 763.65 exponent -3, and I'm going to add that to 606.43 exponent -3, and hit equals. Do I end up with something that looks like 1.37? And I end up, yes, with 1.37. So these numbers are a little more accurate if I use current divider. Here's another suggestion for you. Listen carefully. I would not promote using the subtraction method, and I'll tell you why. I don't promote using the subtraction method because of this reason. if this was a mistake, if we calculated this current, 763.65 milliamps, if this first current was in error and we took the total current and subtracted an error amount, the second number is guaranteed to be in error. You follow what I'm saying? If this first calculation was wrong and you subtracted this from the total, then for sure the second number is going to be wrong. Whereas if you use current divider 2 separate times, current divider for IR1, current divider for IR2, then your answers are more likely to be correct. And you can double check the validity of those currents by adding them up. Do they add up to be 1.37? And the answer is yes. Are we good with the current analysis? We just went through a process. It's called current analysis. We just went through a process called current analysis, and it's a very popular method of analyzing circuits. If we analyze all the currents that flow, these guys are easy to fill in. These are like brainlessly easy to fill in, because according to Ohm's law, how do we find the V? Well, if I go back to my friend Ohm's law, V, I, and R, if I want the V, don't I cover up the V in the circle, and don't I have I times R? Well, do I have an I? Do I have an R for each one of these rows? Can I calculate voltages for each one of those? The answer is yes. So what I'd like for you to do is take a moment, and I will do the same. Calculate the voltage for R1, the voltage for R2, and the voltage for R3. And I will be calling out those voltage values from the gallery of our classmates. So do that now, please.
I have a question.
Yes, please.
The current divider formula, is that associated with any one of the laws we've been working with, or all of them, or is it outside of that concept of Ohm's law and Watt's law?
It is outside of the concept of Ohm's law and Watt's law. Ohm's law and Watt's law helps validate our numbers, but current divider and voltage divider are fractional formulas. And if we take a look at how voltage divider formula was set up, if you recall our friend voltage divider, find a clean piece of paper somewhere here. I have a clean piece of paper. Voltage divider was a fractional formula. It was given, VDF was given as VR1 is equal to R1 over R total times V total. So we call this a fractional formula because this is a fraction. This is a proportion. This is a part of. So if you look at voltage as a pi, your V total as being this much, how much is being chunked out across R1? How much is being chunked out across R2? And how much is being chunked out across R3? So this is a fractional formula. So voltage divider and current divider are, this is a really good question, are outside of Ohm's law and Watt's law, but Ohm's law and Watt's law will always apply to confirm our numbers with respect to these calculations. So this being a fractional formula, I have a total amount of voltage. I'm going to use this fraction to determine what proportion, what part of the total will be across R1, what part of the total will be across R2, what part of the total will be across R3. And by the same token, my CDF, here's my total current, I total, and I have IR1 is equal to RT over R1 times I total. So here is my fraction. This tells me what part of total is going to be divvied up to go through R1. So we find out, okay, IR1 is going to be this much. We find out IR2 is going to be this much. We find out IR3 is going to be this much, and it's all based on a fraction. So the concept behind the current divider and voltage divider formulas is that they are fractional formulas. Okay, good question, Jess. I appreciate you asking. Did that answer your question for you?
Professor, I have a question.
Yes, please.
Does this work on all types of circuits, or is it only ohmic or pure resistors?
So far, since we've only played with resistors and LEDs have not been part of our calculations, the principles apply to everything. Everything we're doing, current divider will apply to more sophisticated circuits when we bring in capacitors and bring in inductors and bring in frequency. The concept is still the same. If I have a parallel, I'm going to divide the current. And there is a method by which we can do that with a little more mathematics than what we're showing here. But the basics of Ohm's law, Watt's law, current divider, voltage divider apply across the board to whatever components we throw into the circuit, whether it's AC or DC. Did that answer your question, Ephraim?
Yeah, I was wondering the current divider formula and the voltage divider formula. They're super useful because you were saying there are other ways to come with the current, more complicated, and this is like super faster way to get to it. But I'm not sure if does it apply for like other types of resistors out there that are not I guess ohmic resistors? That's something that I read early on.
Okay, we won't deal with the esoteric stuff for the time being because this is a first semester class. So we'll leave the esoterica out there because there's negative resistance that you've read about back in week 1. That was part of a week 2 homework. There was a question regarding negative resistance. And so as you look that up, that's one of the more esoteric topics. We won't be bringing that into the discussion of our first semester class. So we'll shelve that for a later course. Is that all right?
That sounds good. Thank you.
Okay, yeah, because I'd rather not confuse the rest of our subjects with that information just yet. It's very good information, but we're not going to bring that in. Just like I briefly mentioned coils and capacitors, that's all I'm going to say about that right now. I'm not going to dive into the solution of this if these were capacitors and coils and something other than resistors. Let's get through this. We have 3 more boxes to fill in. I'm looking for numbers for those 3 boxes. So I am going to call out. Question goes to, let's take a look here. Andrew, do you have a value for VR1 is my question.
20.62 volts.
How many people agree with 20.62 volts? Give me a thumbs up.
No.
No?
No.
What do you have?
11.49.
11.49. Well, okay, we have a disagreement, but let's take a look at the gallery here. First of all, 20.62 volts. How many people give me a thumbs up? 1, 2, 3, 4, 5, 6, 7, 8 people. All right. Tony, you called out 11 and change. 11 and what?
49.
11.49. How many people agree with 11.49? Well, pal, there's not a single thumbs up. So here it is. If you want voltage, remember, according to our circle formula, V is equal to I times R. Do I not have an I? Do I not have an R? Can I just simply multiply this guy times this guy? So all you have to do in your calculator.
Oh, okay. I got the wrong.
Okay.
I timed the wrong one. I timed the total.
I think you. Yeah. Clearly. Okay. All right. So 763.65 exponent -3 times 27. Boom. Hit engineering. Boom. It is 20.62 volts. So 20.62 V. Cool. Okay, so from our peanut gallery, I am going to look for another classmate. How about, let's take a look here. Chisamaga, we haven't heard from you yet. Chisamaga, what value do you calculate for VR2?
I got 20.62 volts.
You got 20.62 volts.
Yeah.
Let's take a look by our gallery. How many people agree that VR2 is also 20.62 volts? Thumbs up? Oh, I see a number of thumbs up. That's pretty exciting. Wow, look at all those thumbs ups. Did we make a miscalculation? Could they possibly be the same? How could we, if you look at, let me go back to speaker view for a moment. If you look at this, I have a different current through the first resistor and a different ohms. Could I take this current times these ohms, get a voltage, have a totally different current, totally different ohms, but somehow get the same voltage? How could that be? Is it too coincidental to be true, or is it simply true?
Simply true.
If something is too good to be true, is it true, or maybe it's false? What do you think?
It's true because it's in parallel.
They share the same node.
Yes. VR1 and VR2, the voltage, I'm going to do this in green, if you will, the voltage across this resistor R2, we calculated as 20.62 volts, and the voltage across R1 is 20.62 volts. Wow. Should they be the same? Well, hey, if they're in parallel, they better be the same. One side of the bank can't be different than the other side of the bank for voltage. So yes, we better have calculated them to be the same. And if we somehow calculated a different value, we're in big trouble. All right, we have one more value of voltage to calculate. And let's see. Hey, Dana, do you happen to have this voltage, please? The VR3?
Yeah, 1 second. 79.46 volts.
79.46?
Yeah.
Volts? Okay, 1.37 times the 58, 79.46 volts. Okay, cool. How many people agree with 79.46 volts? Raise your hands. All right. So we have right over here 79.46 volts. How do we know these voltages are correct? How do we know these voltages are true?
Can you check it with the 15.05 ohm?
We can do that with the simplified circuit, my friends. We can do this with the simplified circuit this way. We knew that this pair of resistors simplified to be 15.05. We also know the total current that flows through this is 1.37 amps. Do we know the current through this 15.05? It's the 1.37 amps. Could I multiply this 1.37 times the 15.05 ohms? Yeah, you betcha. Let's go ahead and do that. We're going to take the 1.37 and multiply by 15.05. Boom, enter engineering, and I confirm that up here I have 20.62 volts. Down here I have 1.37 times the 58, so 1.37 times the 58, and I end up with, down here, 79.46 volts. And if I add these two guys up, do I end up with something very, very close to 100 volts? Plus 20.62, I end up with 100.08 volts, yes? 100.08 volts if I add these two guys up. Did we make a mistake? Are we expecting to see 100 exactly when we add these guys up? Or is this 100.08 because we used rounded off values along the way? What do you think?
Rounded values.
Yes, We used rounded off values along the way in our analysis. So the final addition of these two voltages in this simple redrawn series circuit adds up to be 100.08. I am dancing the happy dance. This is close enough for our final analysis. We good with this concept so far? Cool. This is series parallel circuit analysis, okay, with a parallel and a series component, full VIR. So what have we done in the first hour and 20 minutes that we have been together? In the first hour and 20 minutes that we have been together, we have done two analyses. We did a parallel circuit analysis, parallel VIR, and then we've also done one of these. So let's go back to the share for a moment. Actually, before we do, let's go ahead and give you a quick 5-minute stretch. So everybody, I'm going to put our recording on pause. Pause Zoom recording. And let me switch microphones. Let's go ahead and use this array. So we'll switch. All right, now that we've switched microphones and we're back to looking at the slide set, let's go ahead and continue on here. And the slide set you have already in Canvas. And these are some fun exercises. Suppose you see something a bit more complex like you see in Circuit A. In Circuit A, this again has parts that are in parallel, parts that are in series. And so to the heart of the matter, the easiest way to solve these circuits is to do redraws. What did I say? What word did I just speak? Redraw, okay? Means lots of paper. And so you copy the original circuit, Circuit A. You're not going to copy it now, but I'm just saying, you have a Circuit A, you're going to copy it. And then as you look at Circuit A, what can you simplify? What pieces can be combined quickly? And as you look at that, well, R3 is kind of hanging out by itself. R4 looks like it's underneath the bank, and we can't do anything with R4 yet, but could we do something with the bank of R1 and R2? Sure you can. We just did in the previous example. Can you combine the 28 and the 25? Can you do that right now with your calculator? So pull out your handy dandy calculators right now. Don't wait for me. And calculate the parallel resistance of 28 parallel to 25. So you punch in 28, you hit reciprocal, plus. You punch in 25, you hit reciprocal, you hit equals, reciprocal, equals. I would like an answer from Ryan. What number do you calculate on your calculator?
I got 13.21 ohms.
How many people agree with 13.21 ohms? Okay. That's how long it should take you to do the parallel calculation. It isn't but more than just a few seconds. Use 2 thumbs. It's even faster than a single finger. So if you take a look at Circuit B, does Circuit B show itself as a redraw? And you do take the time to redraw R1 and R2 into what they've called, he's just put down R1, 2. Some people put a comma between them. Some people put a dash between them. Some people will call this REQ number 1. However you call it, it's a 13.21 ohm resistor. Are we okay with the circuit redrawn from Circuit A to now look at Circuit B? What have we simplified in our redraw? Have we taken 4 resistors and simplified it down to 3? Yes? Good with this? Okay. Now, we still have to simplify this further. We have another redraw to do. What can we simplify here? Do we have a pair of resistors on this side in parallel with a single resistor on this side? Yeah. So are we going to do any parallel calculations yet, or are we going to do something else? You should be doing what? If you look at Circuit B, if you have a pair in series, let's just add them up. Anytime you see anything in series, add. Adding is a lot easier than doing reciprocal. So can we just down and dirty add these guys up? What is 13.21 plus the 38? Isn't that going to be 51.21 ohms?
Yes.
51.21 ohms. That's what we calculate. And could we redraw this from 3 resistors now down to 2 resistors? Is this correct? As you look at circuit 3, I now have a combined resistance on this side of 51.21 ohms, and it is now clearly in parallel with the 24. Can you calculate the parallel combination of these two to a single ohmic value? So you take the 51.21 and your reciprocal, and you're going to add that to 24. Reciprocal equals, hit engineering. And what do you confirm? Can you confirm the 16.34 ohms in circuit D? Yeah. This is the method by which you do your redraws. If we had a full VIR analysis to do for this, this wouldn't be hard to do. Okay, it's a little more involved along the way. And let's go ahead. I think that as a good challenge, let's go ahead and do this particular one. I will go ahead and take us off of this screen and now go to, I'll take us off the share. No, I really like the share where it's at. Okay, so if you can see the share and you can see my inset, you're going to do V, I, and R, a VIR chart. And you're going to have 5 rows because there's 4 resistors. Because you have an R1, you have an R2, you have an R3, you have an R4, then you have totals. And you're going to do your 3 columns for VIR. So hopefully in my inset, you're going to draw a VIR table. Could you do that, please? And let's fill in the VIR table with the values in circuit A. What are we given in circuit A? We're given 28 ohms for the first resistor. We're given 25 ohms for the second resistor. We're given 24 ohms for the third resistor. We're given 38 ohms for the fourth resistor. And you're given a total current of 75 milliamps. Those are the givens. So if you look at my inset in our grid, and you're looking at the share screen, did you create a VIR table? Do you have 3 columns? 1 column for I, 1 column for R. Do you have 5 rows? 1 row for R1, R2, R3, R4, and totals. So we have 3 columns, 5 rows. That's 15 squares we have to fill in. 15 squares that we want to fill in with maximum accuracy. Is your table built? Because we're going to be filling in this in just a moment. Now, these were the givens. Now, for the calculated values, I'm going to do this. We ended up with an R total that was 16.34 ohms, yes? So I'm going to write down here, I have 16.34 ohms. We calculated that together, and it does jive with the illustration. Do we have enough information to calculate the voltage?
Yes.
Yeah, what do you need to calculate voltage? I times R, yes? What's my I total?
1.23 volts.
No, my I total is
sorry.
75 milliamps. What's my R total? 16.34 ohms. So 75 milliamps times my 16.34 and engineering. So we calculate a voltage that is going to be 1.23 volts. Is that what we're going to write down? 1.23 volts. Are we good with this so far? Any questions so far? All right. So as we look at the remaining squares to fill in, I need two things in order to calculate a third value. In my first, second, third, fourth row, I don't have two things. I can't take the 1.23 volts, fill in the entire column, because the whole circuit's not in parallel. I can't take the total current, fill in the current column, because the whole thing is not in series. What do I know that we can do? What can we do with respect to this? And I gave you a recommendation earlier. I gave you a method that I mentioned earlier. Leave voltage for the last. What was the method I mentioned to everybody earlier?
Was it the current divider formula?
Well, we're going to use current analysis. Okay? We're going to use current analysis is our method. And yes, current divider is going to figure into this hugely. So in our circuit D, the whole purpose of the redraws is to get finally to circuit D. You want a singular resistance, that's a total. You want the total current, you want the total voltage. Circuit D is done. There's no more analysis with circuit D. So once you've analyzed all the way down to the series circuit, you start taking the information back to the rest of the circuit. What do you see in the rest of the circuit that will help us out? Can we do a current divider in circuit C? Because I have a parallel relationship there, yeah? Don't I know 75 milliamps is going into that bank? Can I find out how much current is splitting to the left and how much current is splitting to the right? The answer is, yeah, I do. I can if I use current divider formula. So I'm going to draw this part out for us, and this will help us out. I'm going to draw this part out because I need to take us off the share screen for just a moment. Okay, and I happen to have 51.21 over here, and I happen to have 24 over here for R3. Okay, I'm going to take us off the share for a moment. And I'm going to go to speaker view. All right, so this is circuit C. In circuit C, I have 75 milliamps coming in, and it's going to be split. Part of it's going to go this way, part of it's going to go this way. So if I want current divider, if I want IR, let's call it the left versus IR to the right. Okay, if I want the resistor to the left, isn't that going to be equal to the R total? What was the R total for these two guys in parallel? Wasn't that the 16.34 ohms that we calculated earlier? This would be 16.34 ohms is the R total for these two guys, and divide by 51.21 and multiply by 75 milliamps. That's the resistor on the left. The resistor on the right, isn't that going to be equal to 24 ohms over, no, I'm sorry, I got too excited. Okay, isn't that going to be equal to my 16.34 as a total, divide by 24 and multiply by 75 milliamps. Could I determine the current that goes through each of these branches? How does this current split up? So do this calculation. To find the current to the left, you take the total of the bank, which is 16.34, and you divide by 5121 times 75 milliamps. I would like to call on Greg. Do you have this current going through this side?
I got 23.93 milliamps.
And he's got 23.93 milliamps. How many people give us a thumbs up for 23.93 milliamps for the resistor on the left? 23.93 milliamps on the left. 23.93 milliamps on the left. And we're not going to use the subtraction method. I would endorse using current divider again. So let's go ahead on the right-hand side, take 16.34, with the total of the bank, divide by 24, which is the ohms of that side of the bank, times our 75 milliamps. And I'd like for this to come from, hey, Anna, haven't heard from you in a while. Anna, could you give us what you calculate for this one, please? How much current is now flowing on the right-hand side?
Wait.
16.34 divide by 24 times 75 milli.
I have 51.06 milliamps.
51.06 milliamps. How many people concur? Thumbs up. There, I see some thumbs up. Okay, so 51.06 milliamps that flows through R3. Wow. How do we know these guys will combine properly at the bottom to show 75 milliamps leaving the bank? If we add these two guys together, are we going to get 75 milliamps? Yeah, you betcha you will. Okay. So this side works out to be 51.06 milliamps, and you add them up. That's pretty close to 75 milliamps. Does one of these currents fill in our current column? Class?
Yes, R3.
Which one? R3. We now know the current that flows through one of the original circuit resistors is 51.06 milliamps. Woohoo! So could I take that and fill that in this cell? I will write down 51.06 milliamps. Bam, that guy's done. Now, how do I do the rest of this? Again, stay with current analysis, leave voltage for the last. What other things can we do to fill in for current? Who's got another idea? Are we done with circuit C? I think so. We've analyzed the heck out of circuit C. There's nothing else to do for circuit C as far as current goes. So if we're done with current analysis for circuit C, can we now take this information to circuit B? And in circuit B, if you recall, we have an R3 on this side, and on this side, we have two in series that come back out on the bottom. So we happen to have an R4 that was 38 ohms, and we have, this is my R equivalent number 1 of 13.21 ohms. So what do I know? I know 75 milliamps goes in the top. I know 75 milliamps comes out the bottom. I know the current on this side, we calculated as 51.06 milliamps on this side. And on this side,
7 volts.
we have 23.93 milliamps on this side. So by taking this information from circuit C and applying it to circuit B, what do we see here that can help us fill in another current? Do we see 23.93 milliamps flowing through the right side as flowing through one of the original circuit resistors, yes or no?
Yes, R4.
R4. We now have this current, the 23.93 milliamps that flowed on this side of the circuit coming down through R4. Ooh. Could I take that value and write it in as the current for R4? Could I write that value right there? 23.93 milliamps. Any questions so far? So far, so good? Pretty darn good. Okay. Are we done with this circuit? What else can we do here? There is something we can do. We can diverge from current analysis. We can quickly do something that'll help us out. If we stay with current analysis, let's go back to circuit A. And in circuit A, we have this. In circuit A, we have this. Okay. Okay, mute your microphones, please, because if you don't mute your microphones, your name will show up on the screen and take over the screen, and people won't be able to see my drawings. So please mute your microphones until I ask you to volunteer an answer. So we happen to have 75 milliamps flowing in from the top. It splits. The current that flows on this side was 51.06 milliamps on this side. The current that flows on this side was 23.93 milliamps that flows, and these two combine to give you 75 milliamps down here. What happens to, that's flowing out of the bank. What's flowing into the bank at the top is 23.93 milliamps. So from the 75, 51 and change goes this way, 23 and change goes this way. Does this 23.93 milliamps split between these two resistors? Could we do a current divider formula to find out how these currents split? Yes, we can. Do we know the individual ohms of these two original resistors? Yes. One side is 28 and the other side is 25. Do we know these two combined is 13.21? Can I do current divider to find these currents? Carlos, can you help me find the current that flows through this part of the bank? I have 23.93 milliamps coming in. My current divider formula, and I'm going to write this out here. This will be IR1 is going to be equal to, and write down the general formula, RT over R1 times IT coming into the bank. What I'm going to fill in is for the bank. What is my total for this bank? If I have 28 parallel with 25, we combined this earlier. Isn't that my 13.21 ohms, Carlos Navarro? Carlos?
Yes,
Unmute your
sorry,
microphone.
I was having trouble unmuting. That's correct, right? So that's our first value, 13.
13.21 was the total for the bank, so it must come here in the numerator. So I'm going to write down 13.21 is my numerator, and the R1 value is 28, and my total current is not total current for the circuit. Remember, the total current for the formula is what's total coming in, and how much was coming in was 23.93 milliamps. 23.93 milliamps. So what do you all, everybody make this calculation? 13.21 ohms divide by the 28 ohms on this side of the bank, multiplied by the total current coming into the bank of 23.93. I'm going to do this calculation off to the side, and I'm going to call for an answer in just a moment. Divide by 28 times 0.3393 and engineering. So the total current, I'm going to ask, Erica, do you happen to have this value for us? This current divider? The current that flows through R1. Erica? I would do 13.21 divide by 28 times the 23.93 milliamps. What do you think? She might be away from her microphone. Benjamin, what do you think? Kirsten, what do you think?
I'm sorry, I'm not sure.
Okay, can you see my calculations? Can you see
Maybe
my
11.28.
Can I take a stab at it? Yeah.
Yes.
11.29 milliamps.
11.29 milliamps is correct. But I want everybody to understand and not just write down a number because we say it's correct. How do we get and confirm the 11.29 milliamps that is flowing through this side of this parallel arrangement? I know the current coming into the bank is 23.29 milliamps. Is everybody good with understanding how that current on this side is 23.29? It came from our simple circuit in circuit C. The 75 milliamps split to be 23.93 milliamps on the left side of the circuit. That 23.29 milliamps flowed through these two resistors on the left side of the circuit. That same 23.29 milliamps is what flows into this bank of two resistors. And that's the IT that is going to be split between these two resistors of the bank. My current divider formula says I'm going to calculate the R total for the bank, divide by the ohms on that side. So it's going to be my 13.21 ohms, which is the total of the bank, divide by the 28 ohms of this branch times this current. And if I go through this, 13.21 divide by 28 times 23.93 milliamps. Erica, were you able to confirm this number? Benjamin, were you able to confirm this number? Kirsten, are you able to confirm this number of 11.29 milliamps?
Yes, now I am.
Yeah, me too.
Okay, cool. All right. So we end up with 11.29 milliamps on this side. How much current goes on the other side? Well, mathematically, all you need to do here is my IR2 is going to be equal to the total of the bank, which was 13.21. So 13.21 divide by the ohms on this side, which is 25, and multiply by the current coming in, which is 23.93 milliamps. So times 23.93 milliamps. So let's do this calculation. 13.21 divided by 25 times 13.93 milliamps. And the calculation goes to Chisamaga. Do you have a calculation for us?
I'm still putting in my calculator right now.
Okay, I just did. So what do you have, Chisamaga? $13.21 divided by 25 times 23.93 milliamps coming into the bank equals
12.64 amps.
12.64. Look at the power of 10 on your far right-hand side. What's it show you on the far right-hand side?
It says 0.
Okay, and that's the reason why it says 0 is you forgot something critical. You forgot to key in milliamps. You just multiplied by 2393, and you can't do that. 23.93 exponent -3. You can't forget the milli. You can't get lost in the big numbers. You got to look at the details. And so although the numerals are correct, the numerals are clearly 12.64, you have to remember to key in milliamps and you will get out milliamps right there. Are we good with this so far? Cool. That is current analysis. What did we say for last? Voltages. And voltages are just nothing but I times R. So let's go ahead and multiply these numbers, these I's times these R's, and let's see what we get. So the 12.64 milliamps times 25. $316.12 millivolts, 11.29 exponent -3 times 28. 316.12 millivolts, 51.06 exponent -3 times 24. 1.23 times 24.23 volts. Correct. And then finally 12393 times 38. 909.34 millivolts. Once you have all the currents, you multiply by the ohms, and you get and be able to verify these voltages. This is a really good exercise in VIR for a rather complex 4-resistor circuit. This was a VIR that we had done earlier for a 3-resistor circuit. And we had also done a VIR for a parallel circuit. So we've done 3 VIR analyses. What you're going to be doing with all of this is you're going to be building these in your lab. And let me take a moment and talk to you about your lab. Before we do, are there any questions about these calculations? You're just going to have to practice a few more to get the hang of this. But we're going to be able to verify all of this in lab in just very shortly. Okay, I'm going to go ahead here and all right, can you hear me now? Am I coming in clearly? Hello, hello, hello?
I can
Hello?
hear you, but
Yes.
you're
Okay.
moving your mouse, right? Oh,
Can you hear me clearly?
Yeah.
Okay, all right. Even though, yeah, I'm getting an error message on my screen, but I wanted to make sure you can hear me clearly. All right. One of the most exciting things that will happen this week for you is you're going to be introduced to something called TINA TI. And TINA TI is a circuit analysis tool that you can download for free as long as you are using a PC. If you are using a Mac, you are out of luck. You're going to have to get your hands somehow, some way, borrow a PC for downloading this software because it is for free and working out your solutions in this software. The information for this is in your week 4 of Canvas. And let's take a look. Let me go ahead and share the screen. Here, share screen. And I want this screen to share. Okay, can everybody see my Canvas screen? In the Canvas screen, in week 4, you will see that we have TINA TI software. If I click on TINA TI software, opens up that particular page, and there is a download instruction in PDF format of how to do the download. We're not going to do the download together. You're going to do that after class. You're going to do that sometime between now and Thursday. It's a fast download. It doesn't take very long to do. The download is, if you follow the directions, you'll be able to get the software and everything works beautifully. What I'm going to show you how it works is here. I'm going to go off of this share for a moment and go here and press TINA TI on my computer. And let's see where it lands us. TINA TI. Coming up, coming up, coming up. Okay, it lands us on this screen, so let me move this to my secondary screen. And now let me go ahead and do the share on it. So schematic editor, I want this one to share. Cool. Can everybody see my TINA TI screen? I'm going to maximize this and I'm going to zoom to 200%. Okay. This is a remarkable tool. I happen to have a number of different electronic components, these symbols you're familiar with. This looks like a ground. It is a ground. This is a voltage source. So if I click on this and I place this guy right here, can you see a voltage source on my screen right now? Cool. I'm going to move it here and I'm going to grab a resistor and I'm going to move it. Let's see, I want to do the second circuit that we built. I need 3 resistors. So I'm going to put 1 resistor here. I'm going to click on another resistor, put it here. I'm going to click on a 3rd resistor and I am going to put it here. So I have 3 resistors and I'm going to bring in a ground. And I'll put it in a ground somewhere. Can you see the 3 resistors, the voltage source and a ground on the screen? Give me a thumbs up. So far, so good? Okay. The orientation of R1 was vertical. So if I click on R1, I clicked on R1. Do I have an arrow up here that rotates to the left, rotates to the right? Okay, so I'm going to rotate this to the left. Take this one, rotate to the left. Okay, so now I've got two of these, and this is in the correct orientation. Take this guy, rotate, and that's really good. Okay, so now I've got three resistors in the appropriate orientation. I'm now going to use my mouse. My mouse is an arrowhead. When I go to touch the very top of my voltage source, the mouse changes to a pencil. And if I touch the tip of the pencil to the X where my voltage source is, in fact, let me magnify this just a little bit further. I'm going to go to 300 and hit enter. Can I go to 300? 300 and enter? No, I can't go any further. Oh well. Hopefully you can see this. The tip of my pencil, I'm going to click here, come up, and connect here. So now it's connected, oops, to that first resistor. I'm going to click on this guy, come over here, and click. Actually, I want to do things a little differently. I want to make this look a little bit more like this. These two guys are clearly connected. And I'm going to come up here, come over to here, come down, and click there. That's a better arrangement. I'm going to take this guy, come over to here, come up, and click. Click there. This resistor is going to come down just a little further, and I'm going to come up and click there. I have a node. I'm going to take my ground, move this a little further over. Oh, my voltage source is a little different. Disconnect this wire. My voltage source was negative plate on top. So I'm going to take this guy and rotate, rotate. So now it is negative plate on top. Take the pencil, come up, over, and down, and click. Cool. Take this guy, move this down here. Take this guy, come over here, and down to the ground. And that's attached. And this guy down. Cool. Okay, so does this kind of look like the second VIR table that we put together? All right. We happen to have, if I double click R1, I have a little table. And right now the value defaults to 1 kilo. I'm going to make this guy 27 and hit enter because we had a 27 ohm resistor. Double click this guy. This defaulted to 1 kilo. I want to make this a 34 ohm resistor. I type 34 and I hit enter. The R3 again defaults to 1 kilo ohm, and R3 was 58 ohms. So 58 and enter. The voltage source with here was 100 volts. I'm going to double click my voltage source. It shows us 5. I'm going to type in 100 and hit enter. So now is my voltage source 100, R1 27, R2 34, R3 58. So far, are we good with the circuit build as matching what we have? We've done a lot of work. So I'm going to come up here. I'm going to do a file, save as. Got to save this. So in the file save as, I should have a nice dialog box here in a moment. Hello. Where'd my dialog box go? I bet you it's hidden. It's hidden behind my Zoom screen. There's my dialog box. Okay, let me move my dialog box here and move my Zoom screen back where I can see it. There we go. Okay, I'm going to need to put it someplace where I know I can find it. So I'm going to here, and I know I want this on my thumb drive. And on my thumb drive, I already have a folder I've created for Tina TI. So Tina TI. And this one happens to be, I have a number of circuits here already. I want, okay. I will call this SER-1 PAR, series parallel, space 3R for 3 resistors, dash KO, because that's my initials. So you're going to put down your initials because you've got to name it with whatever you name it as. So it should have your initials. And I'm going to hit save. So now we should see that name appear in the title bar. The title bar should show SER-PARs for series parallel, 3R for 3 resistors, dash your initials. And I put down KO. Got to save it. Now, we did some calculations. We did a full-on analysis of currents. We did a full-on analysis of voltage. Let's go ahead and verify the voltages first. Let me show you how to do that. Right here is a voltmeter. If I put this mouse over to here, hover, and it shows voltmeter. I click on voltmeter, and I'm going to bring in a voltmeter. Bam. Now, as I look at this, before I attach my voltmeter to this bank, what is the polarity of the resistors at the top of the bank? Look at the polarity of the voltage source. Which is the plate on top of my voltage source? What polarity? Tony, what's my polarity on the top of my voltage source? Tony.
Negative.
Okay, so the top of my resistors is what polarity?
Negative.
Also negative. So that means before I hook up my voltmeter to this, I have to have the negative side of the voltmeter on the upper side of the circuit. Right now, positive lead is here. So what should I need to do with this voltmeter? Probably rotate it and rotate it one more time. And if I rotate it this way, do I now have the positive lead that I can connect to that part of the circuit? Do I now have the negative that I can connect to this part of my bank? Do I now have a voltmeter across my bank? So far, so good. I'm going to bring in another voltmeter because I want to verify the voltage across R3. Come up here, select voltmeter, bring it over, and I'm going to place the second voltmeter here. And again, I'm going to have to flip this guy upside down. So I'm going to flip by rotate and rotate, and then grab it and move it down here. So there's my next voltmeter. The positive side, I'm going to connect to the bottom of this resistor. And the top side, I'm going to connect to the top of this resistor. So now, do I have a voltmeter to the bank? Do I have a voltmeter to the third resistor? So far, so good. And I said we were going to check on voltages. So quick and dirty, I'm going to come up here to where it says analysis. And if I click on analysis and I go to DC analysis and I come over to table of DC results, click. I have a table of DC results. And I'm going to expand this table. And let's take a look at the voltage for VR1. So voltmeter number 1, right here, voltmeter number 1, so VM1 is across this bank. What did we calculate earlier in our second VIR chart for the voltage across R1 and R2? Did we not calculate 20.62 volts? And what does the voltmeter, what does the analysis show us here? 20.6. It didn't show us the second digit, but that's pretty good, 20.6 volts. It verified our calculations, eh? Now, you don't have a 100-volt source on your breadboards. You have a 5-volt source, but do you have a method now using TI to now go to any value of resistor, any value beyond 5 volts, and verify with your analysis using TI to determine these voltages? Yes, you do. This is a remarkably powerful, powerful tool. Let's take a look at the voltage across R3. We calculated R3 earlier, 79.46 volts. What's it show us? For VM2, voltmeter 2 is 79.4. Are we good with that? Very, very good. 79.4 volts. And that's what you want to verify, is just look at the voltmeter readings.
How did you get to that table again? You clicked analysis?
Okay, how do we get to the table is once this is all built, and you got to make sure it's built and that it has nodes in place. If you got a wire connecting here and you don't see a node, you don't have an electrical connection. So you got to make sure you see nodes. Once you see the nodes are in place, you come up here to the menu bar, you click on analysis, and then you come down to DC analysis, and then you come over to where it says table of DC results. And I click on table of DC results. It comes over here, bring this over, and you can grab the bottom of this, pull this down so you can see the voltmeter VM1 and VM2, and the values correspond for VM1 and VM2. Are we good with this so far?
Professor, when one goes to the Canvas TINA software, it says that the access is denied. I don't know if it's just me or is anybody else getting that.
Yeah, that happened to me too.
What access? Access to what? The PowerPoint for?
No, the whole download.
Yeah, the instructions.
I saw that too.
You have to like approve us access for it.
Did you create an account?
I don't even think it gives us that option.
It's your PDF, Professor, that you have instruction for us how to download that we
Yes.
can't read.
Oh, so you can't read the PDF is what you're saying?
That is correct.
Yeah.
Okay.
Access denied on Canvas.
Okay, that's a different thing. We can solve that in a moment, but thank you for bringing that to my attention. Let's go ahead and finish this guy up. I actually don't want you to be too distracted with trying to do a download and trying to watch this video, trying to watch our lecture at the same time. But thank you for bringing that up. I will fix that easily. Now, one thing you're going to need to do to prove that this is yours is you are going to hit the little T box, T for text, and it opens up a text box. And what you're going to type in is the name of the circuit, which is series dash parallel, oops, parallel 3R dash your initials, or you can also buy, I'm a sample, and hit the little font button. Go to make this bold and go to make this, let's say 20 point type. So make it bold, make it 20 point type. Blue is fine. You can pick any color you want. There's a lot of colors to pick. Blue is easy. Hit OK. And then if you're happy with the way it looks, hit the checkbox and it'll place it on here for you. There you go. And let's make sure the analysis is still there. DC analysis, table of results. Bring that table in and then bring this down. And cool. Is everybody seeing what we have here? Have the circuit built, you have the table that shows the analysis, and you have a label. Can you take a snip of this screen? Because I don't want you to send me the TINA circuits. I just want to see that you've built the circuit, you've got it named. Just paste this into a Word document, paste this into a Google page, whatever works for you. Paste it in somewhere so that I can open it and you can demonstrate to me that A, you can build the circuit, B, that you can build it properly with the meters, C, that you can prove the measurements based on our calculations by virtue of the value being clearly stated in the table of measurements, and also that you can put in a text label that shows that you have done this. I'm going to put you on mute for just a moment. I have to take this call. Excuse me just a moment. So let me go ahead and put us on mute and put this on mute. And hi, can I call you back in about half an hour? Is that possible?
Sure.
I'm in lecture right now. Thank you.
Okay.
Okay.
Sorry.
No worries. Bye.
Bye.
All right. Okay. It was not an emergency. I have someone had asked, "Hey, Co, how come you're behind on your grading?" Well, I have a 92-year-old mother-in-law that I'm one of 3 caretakers for, and 4th of July also happened. So as I exercise a little flexibility for you in turning in assignments late, be a little flexible with me in grading all of your tasks so far. Okay. All right. So that being said, can you do a snip of this? So I'm going to come here and do a screen. I don't want to do a screen. I'm going to do a snipping tool, hit new. So I am going to, with my snipping tool, come over here on the screen, grab this part of it. I don't need the menus. I don't need anything other than this part right here. And I then copy this guy. And I go to either a Word document, or I'm going to go to Pages or something, File, New, blank document. Give me a blank, paste. Is it there on a page that shows clearly what we built, what it is, who built it, and we've got some values? Yes? Okay, so you have some things to do between now and Thursday when we meet again. And what I encourage you to do is to look over 2 YouTubes. One of the YouTubes was from our study session yesterday. We had a great study session. Some of you had joined in on the study session as part of a study group. Kirsten formed the study group, and then Abbas and Kirsten called a meeting together that didn't quite happen on Sunday. And so I jumped in and said, okay, well, why don't I host the Zoom and let you all have that session where you can chit chat with each other live. And we had a good session. Somebody had asked, well, how long is that session going to last? And I said, well, the session could be 15 minutes. If you ain't got any questions of me that lasts longer than 15 minutes, or it could be longer. And it turned out to be almost 2 hours, as it turned out. It was a really good study group yesterday, and a lot of good questions. So that study group YouTube is already posted in YouTube and already posted in your record as a link. So do look at that. If you were not part of the study session, I encourage you, if you take a look at the discussion board for week 3, and I apologize that I didn't see that it wasn't switched on. Someone had brought that to my attention that, hey, Co, the discussion board for switch 3 wasn't switched on, and it wasn't brought to my attention until yesterday. So I switched it on, and I also put in a reply that people can respond to. And the discussion board has to do with Discord, asks you some questions regarding Discord, so respond to that. And so since it didn't get posted or didn't get activated until yesterday, you have some leeway in responding to that discussion board. It will not be late, okay? Okay, so what you need to look at will be the video from yesterday from the study group that put together some really good questions for me. We did a really good analysis of circuit G voltages at different points, for the open switch voltages at different points, for the closed switch. So it's really good discussion there. And as soon as I get the as soon as I get the Zoom recording, I will put it in the editor. From the editor, after it's edited, I will put it into YouTube. But for the time being, let me check on Canvas. So let me stop this share. Let me check on Canvas what I need to check for your access, because I can paste another guy in there. And I think that's what I need to do. Very simple solution to that. And once you get to the PDF, then you'll be able to
I could open it.
Yeah, it works for me.
Nice. Okay, so once you're able to open the PDF, it walks through the different steps of what you need to do. I won't go through those steps because you can look at that on your own. What you do need to do is you have to create a Texas Instruments account. That's really easy to do. You just go ahead, give it a username, you give it a password, and keep your passwords consistent, the easier. So the next time you open up Tina TI, it is free for anybody who uses a PC. As I've said, this will not work on Macs. A lot of the software in the sciences simply will not work on Mac unless you happen to have a PC emulator for your Mac. But if you don't have a PC emulator for your Mac, then you're going to need to find somebody to borrow a PC, laptop, something with in order to do this exercise. So now that you, yes.
Quick question. I don't know if it was mentioned, but is that just for this week's assignment, or will we be using this program further down the road? Or
oh, you're going to, yeah, well, it's free to you. You're going to be using this for weeks to come. Okay, because I don't have a PC, so I'm trying to figure out what I'm going to do. I have all Macs, and I don't really know anybody with a PC. So okay, you're going to have to think about some way. It's a portion of your grade points. If you don't have access to a PC and you don't have, then you can do this on paper, and you can at least get credit for the analysis on paper. So that'll be part of what you can do in order to get partial credit. But the learning experience is really playing with a circuit simulator that allows you to expand beyond the 5-volt source that we have on our breadboards. Okay?
Okay, thanks.
Okay.
So if we don't have access to a PC, we can do it on paper?
Yeah, there's only so much you can do on paper, though. We've already done this on paper, right? We already did this analysis on paper. So in future circuits that I'm going to give you as exercises to do, yes, you can do future series parallel exercises on paper, and you're gonna, but it's nice to have the circuit simulator in order to verify your calculations for current and verify your calculations for voltage. It's just it's just have your voltmeter and they have your breadboard. You do the analysis for all the breadboard circuits done. You also build the breadboard, and you can also measure it with the digital multimeter.
Professor, we can't hear you. Sorry.
I'm sorry?
Your microphone.
Oh, sorry. Let me go to a different microphone. This guy here. Okay, let's try a different microphone. All right. So that being said, where was I? Yeah. Okay, so for future circuit analysis, you're going to have plenty of series parallel to do. If you don't have the circuit analysis to double check your calculations, then the best you could do is just do your calculations on paper and you can get partial credit, okay? So you shouldn't be penalized for not having a PC, but because you don't have a PC, you're not able to enjoy the full benefit of double checking your answers using a tool that is remarkably powerful and is a standard of all of our sciences that in the sciences department that and you can do this on a Mac. As I said, you can, as long as you happen to have a PC emulator for your Mac, and some friends do have a PC emulator where you can run PC programs on a Mac. That's not that the people have been doing that for years. So if you haven't learned how to do that, then you might want to check on some YouTubes or check with some friends who also own Macs. Birds of a feather flock together, and check with other Mac owners and say, hi, what have you used as a PC emulator for your Mac? And once you have, it might be a virtual machine that you load up. And then so as part of the hard drive of your Mac, part of that hard drive is devoted for PC functions because you're using a virtual machine within Mac in order to do PC exercises. And once you create that volume of space on your Mac hard drive to run PC programs, you can install PC programs, you can run PC programs. So that is nothing new with respect to Macs. People have been doing that for years. So if you haven't done that, do definitely explore that, because you really don't want to miss out on the fun of double checking your work using these circuit simulators, okay? So for those of you who have Macs, there is a solution, and that's known as a PC emulator. Virtual machines, something of that sort.